Hello, everyone, and thank you for attending this talk. Our work is accepted as a poster paper. However, in this talk, I will try to give you the bigger picture. Runtime verification is a formal method to verify a run of a system with respect to a specification. The program code is usually instrumented to extract events that abstract the execution into a trace that is fed to a monitor. One of the most prominent challenges in RV is the runtime overhead introduced when augmenting a system with runtime verification. The overhead is caused by the added instrumentation code inserted into the program to produce events. Combining static and runtime verification seems natural. In one direction, RV improves completeness of static verification by deferring the verification of undecidable fragments until runtime. In the other direction, static verification reduces the overhead of monitoring by pruning pieces of the program that can be statically analyzed. Our goal is to combine static and runtime verification. So we present a way to statically find safe execution paths in the program. Such paths are guaranteed to preserve the monitored property and thus can be ignored at runtime. We guide the instrumentation tool to only select program points that need to be observed at runtime, and end up monitoring only residual parts that static verification fails to prove safe. We'll start with a motivating example. Let's say we are interested in monitoring a safety property regarding iterators in Java, which specifies that a collection should not be updated when an iterator associated with it has been created and being used. In this program, we have two lists and two iterators being created and used. Now we ask ourselves, does this program violate the property at runtime? Now, before answering the previous question, let us look how monitoring is achieved. Many monitoring approaches rely on the detection of bad and good prefixes. These are witnessing sequences allowing a monitor to conclude its verdict as early as possible, based on the trace it observed so far. To monitor the safety property, we need to look for bad prefixes at runtime. In this example, if we observe a sequence containing a create event followed by an update and the next event, then the monitor reaches the accepting state and we conclude that the whole run violates the property. However, in real life, multiple variables in a method may produce the same events. Hence, we have parametric monitors that are specified with a variable binding, and events that are accompanied by runtime information. You can see that each event has its variables mapped to a runtime object. For each unique binding, a monitor is created and the traces are projected accordingly. You can see how the projected traces are different depending on the relation between L1 and L2. Now let us get back to our question. And the answer is yes. If 1, some flag evaluates to true, and 2, if variables L1 and L2 alias each other. Because you can see that at lines 10 and 11, L2 is being updated, and if it references the same list object as L1, then this is a violation of the property. Now we ask a more interesting question. Can we fully verify this program statically? If yes, then there's no need to instrument and runtime monitor it. Assuming some flag condition is only decidable at runtime, we need to perform pointer analysis to check whether the variables L1 and L2 are related. The pointer analysis will return one of 3 results. However, in practice, pointer analysis will often time out and never return any result. To answer our question, we need to get the result that L1 and L2 must not alias. This is sufficient to statically ensure that the method will behave correctly at runtime. Now here are some observations we made. Pointer analysis may not always conclude with the result, especially for Java programs. The main problem is the inability to construct the full static graph of the program. Our work relies on the idea that we can over-approximate the program behavior and still benefit from some static verification. One can safely assume that such two variables from the previous example may alias, even without performing pointer analysis. Moreover, we can analyze single methods separately. However, we need to handle escaping references. A variable we are interested in may escape from a method to a subroutine or a return statement and produce events there. Now we move to discuss the work we did. Our approach consists of two steps. Statically, we first capture the program behavior in step 1. Then we try to find violating paths in step 2. Finally, the program is instrumented to monitor at runtime only the residual parts. We start with capturing the behavior. Given some property and assuming we have the control flow graph, we map instructions to events. We keep the instructions that produce events for our property. We also keep instructions that may allow any variable to escape. We then discard all the remaining events. After that, we generate an automaton from the CFG. The mapped instructions are now the transitions of the automaton. The CFG automaton will now allow us to analyze all different paths that the program can take. Now we move to cutting the behavior. To handle our over-approximations, we need to extend the language of bad prefixes. Recall from our previous example that different variable aliasing may produce different projected traces at runtime. Since we assume that all variables may alias, the path in the CFG automaton may be polluted with unrelated events. To safely handle the different projections at runtime, we use the upward closure of the language of bad prefixes. The upward closure of language allows us to recognize subwords of the accepting words of that language. We append the bad prefixes automaton with sigma self loops. You see now that the automaton would accept all possible projections of traces. Now also we need to handle escaping events. We need to assume that an escaping event might produce events untracked by the method we are analyzing. We need to incorporate them in the language of bad prefixes. We add an escape transition in the bad prefixes automaton from each state to all of its reachable states. And now our extended bad prefixes automaton looks as follows. We now proceed to describe our main algorithm that finds violating path in the method. The algorithm takes the CFG automaton and the modified bad prefixes automaton and performs model checking by finding intersection between both automata. The main idea is to traverse the constructed CFG automaton state by state and check whether there is a path that makes the bad prefixes automaton reaches a final state. The algorithm returns a set of safe states and a set of possibly violating states. Now we show the result of the algorithm. The red nodes are the states that we need to instrument to monitor at runtime, and the green states are safe states that will be hidden from instrumentation. We can see that instead of instrumenting at 8 different locations, we reduced instrumentation to 4 locations only. We implement our work as a plugin to BISM Java bytecode instrumentation tool. We extend it with a module that generates the automata. For each property, we then write 2 BISM transformers, a static analyzer that allows us to run our algorithm to mark safe instructions, and a transformer to instrument the residual parts for runtime monitoring. We now report on our evaluation of the effectiveness of the approach. We compare the instrumentation overhead with and without residual analysis, denoted by RRV and RV in the table. We instrument with BISM the benchmarks in the DaCapo suite to monitor the safe list iterator property, and a similar property for maps. The experiment shows a reduction in the instrumentation points by a factor of 2 on average, reaching a factor of 6.5. A reduction in the number of events generated at runtime by a factor of 1.6 on average, reaching a factor of 2.5. Thank you all for your time, and I will be pleased to answer any question.